Well, thank you everybody for joining our presentation today. We're talking about optimizing Ceph for AI and ML workloads. Kind of overview of the status quo, kind of a little bit of a history lesson, and also go into some of the stuff that we've been planning. So I'm Kyle Bader. I'm a principal portfolio architect for Ceph offerings at IBM, and then.
I'm the engineering manager for Ceph Object Storage, now at IBM.
All right. So first, we're going to set the stage with a little bit of a background. So a lot of the work that we've done with data lake, analytics, and AI and ML was really driven by practitioners, right? So we had, with Ceph, we had block, file, object. Object was added early on, and in about 2007, we had several users that we were working with who were trying to use Ceph as an object store for analytical data, and we really wanted to find out more about what they're trying to do, and find out more about the environments that they were using. That this data was originating from, and the tools that they were using. And so we set up a workshop. And so we gathered up individuals from, at the time, we were at Red Hat, so Red Hat, and then 4 different customers from different verticals. So we had a healthcare customer, we had a financial services customer, we had a telecommunication customer, and a big retailing customer. And we all kind of came together, and all of them talked about how they were using Ceph object storage and what their big data environments looked like, what tools they were using, what data formats they were using. And we really wanted to identify the workflows, the tools, so that we could then figure out the needs of these workflows and start to prepare Ceph for a future where it can be used as a data lake. So this is back in 2007. Yes, 2017. 2007, that would be really future forward of us. We were not that. Okay, so fast forward, this is kind of the landscape of today, where most people at this point have disaggregated their storage from their data processing environment, and oftentimes that data lake is in object, blob store, that sort of thing. This is even more interesting now because you're starting to see that people have different types of data processing environments. They have kind of general purpose data processing environments, but then they also have clusters that have very specialized hardware accelerators that can be used for inference and training and doing other sorts of special purpose computation. And you really don't want your storage to be co-resident with these things because you want all of the available resources on those machines to be able to be dedicated to the tasks. You don't want your training to be running slow because it's doing a bunch of work to run a storage cluster, right? You want that broken off onto a separate infrastructure. So beyond just features, there are like many dimensions of scale that come into play with analytical processing. And one of the reasons why object storage was very attractive to folks in moving away from, say, something like HDFS was with HDFS, there were some very real limitations about the number of files that a name node could support. And while you could take multiple, they started to generate capabilities where you could have multiple name nodes and you could do kind of a federation. A lot of folks preferred the simplicity and the flatter structure of an object storage based approach. And so we did a lot of work to really push the metadata capabilities, right, so that you could store billions and billions of objects. And I think if you were here, I'm not sure if it was earlier today or yesterday, the Bloomberg presentation, they mentioned that they had 20 billion objects in their cluster or something like that, right? We have done testing to where we've put 10 billion objects in a 6-node cluster, right? So we've really, really pushed And that 10 billion objects wasn't, 10 billion objects is one thing, right? But doing 10 billion objects on 6 nodes means you have over 1 billion objects per node. And just because of the way that Ceph is architected, as you scale out the cluster, 10 million isn't the upper limit of the system, right? It's algorithmic placement. We've also pushed the dimension of scale when it comes to number of objects within a bucket, right? I think the most that I've personally ever done was I put 250 million objects in a single bucket. Now, granted, you probably shouldn't do that, but we're really trying to push all the different dimensions of scale because these sorts of workloads demand that sort of thing. We've done a lot of tests, pushed the aggregate throughput, right? I think it was a couple years back, we did a 10-node disk-based cluster, and we were able to push it to 80 gigabytes a second. And as we've continued to do the at-scale testing, through the Gibit cluster testing with the new releases, where we're testing higher and higher numbers of OSD counts in a single cluster, and as the capacities of drives continue to trend upward, we're now looking now decapetabyte is not even a lot anymore, right? It's very, very real to get into the higher tens of petabytes or even up to 100 petabyte in a cluster. There were a number of features beyond just being able to push the dimensions of scale that we started to put in because we felt that they really tied in and married well with these sorts of workloads, right? So we were watching big data practitioners that were starting to adopt object stores and listening to the things that they said they were doing in order to prevent for their use cases. So we heard, oh, we're turning on versioning so that if somebody accidentally does something that we can recall a copy of the data. We're also putting in MFA delete so that we don't actually, because even if we have versioning, a rogue application could be deleting the old versions as well, and that could be problematic. So with MFA delete, you need, in order to delete the old versions, you actually need an MFA token. Kind of makes it more bulletproof. And then object lock, bucket notifications. If you're in my last presentation, talked a whole bunch about that, and IAM policing, the sorts of interesting things you can do with that. S3 select, which is basically computational push down to the storage, and then the more sophisticated access control, which I won't get into. So one of the big things that kind of brought this all in was the S3A file system client. So this is kind of the really quick how you basically use it. But the most important thing I think with all this is that in a lot of cases you weren't interacting necessarily with objects. You were using some sort of table abstraction like Hive, and then behind the scenes it was using the object store. So the actual data analysis that were consuming data weren't interacting with an object store at all. They were interacting with tables, and they didn't know better. And that's kind of the most powerful thing, right? Is you can have these tables, or you can have these, or you can have tables or databases or even partitions of tables that are mapped to different buckets that could be in different clusters or different locations. So some of our big data lake customers, they might have multiple clusters, but it doesn't matter to their data analysts because it's all abstracted away through Hive. Now, there's some really interesting quotes that I've seen recently, right? So OpenAI, they did a blog post within the month where they were talking about really large Kubernetes clusters that they're operating. And I thought it was really interesting that they were saying most of our jobs, they just interact with blob storage. Right? They're not interacting with file systems. They're not interacting with block devices. They're interacting with object stores. And for a lot of the reasons that I've detailed. If you look at Meta published a paper on large-scale recommendation systems and the infrastructure around them and the data processing. And they talk about feature flattening, right? So feature flattening is basically where you have a bunch of data in a table, and then you're not going to train off of all of the data in the table. So you take or you compute features from that table, and then you store the result, and then as TF record files or record IO files, and then you actually do training off of that. I think Mark has a good talk later today where he talks about the benefits of using these sorts of formats for training and inference. But anyways, kind of these major AI practitioners, they're not talking about using file systems. They're not talking about using block. They're talking about using object. All right, I'm going to pass it off to Matt, and he's going to talk about our alliance with Massachusetts Open Cloud.
Yeah, okay. So I'm going to try to do in the last part of the talk is cover two things. One, essentially our research collaboration that was convergent with the work that Kyle and his teams, and customer teams were doing with object storage and S3A, which is around almost the same time, around 2017. Research professors from Boston University and Northeastern University, which is sort of the leaders of Massachusetts Open Cloud, but there's other universities in there too, obviously. And their PhD students started working on ways to accelerate high-value analytics workloads running on top of S3. So I want to tell Ron Krieger and Peter Desmeyers are the professors, and there were three primary students, but Ur Kanar wrote a dissertation on something called D4N, which we'll talk a little bit about, which is a converged S3 object cache for accelerating interesting workloads. And Mania Abdi wrote a dissertation called Queries, which talks about an intelligent prefetcher to make that cache extremely efficient, even though it is otherwise, it would tend to be, as an intermediate cache, it's going to tend to have low hit rates for a variety of workloads in a data lake. But with prefetching, with the intelligent prefetching that they conceived, that's inverted and it becomes extremely efficient. So D4N, is the so-called directory-based data center delivery network, a big long name there, is this elastic converged S3 object cache. The directory, this is all kind of a bunch of details, but the directory piece is interesting to us because it's part of how we extend the architecture of Ceph RGW to have a much richer store of ephemeral metadata and some other things. For read and write, so yeah, it's a write-back cache. And then Queries, I'll tell you a little bit about that. This was quite exciting to me. The Queries method was based on, I think, analysis of a system called Pig, a Hive system, but then also is extended to Spark. Both of these systems, and they're not unlike others out there. There's a workload analysis and scheduler component to these systems. And in the case of Spark and Pig, they're both called DAGs, directed acyclic graphs, of the work plan for the query, which includes information about what objects are going to be used and in what sequence of the work plan and how long that, some other facts about how large that work cycle might be. So starting from that, what Queries does is it injects itself into the DAG system of say Spark, intercepts those DAGs in a central location, and from it and uses a variety of techniques, but one is a critical path analysis of the graphs, so that they can produce a common optimized path through the data sets that are going to be analyzed in what sequence and understand what element should be in cache at what time. Before any of the work is actually executed, so the prefetcher executes before the work. So it's a highly optimized pre-staging of data in the cache.
Yeah, and if you've ever used Spark before, you can think of it as, when Spark, the Catalyst engine, is doing the query plan, and so before the Spark workers even start asking for the objects, basically there's been pre-fetching instructions that have been sent down to Ceph, so that before that worker even requests the object, it's already been materialized in cache, so that when that worker finally does request the object, instead of having to be read from disk, it's just coming straight from memory at that point.
Yeah, so there's quite a bit of work that went past that. So there's also a write-back component, and it does a number of things. One thing is that some types of systems, including Hadoop, but probably also Spark, there are some types of jobs that will produce ephemeral data, whole buckets full of it. In the case of Hadoop, this stuff never has to get written back to the main data lake. In fact, it can be discarded after it's used. They also, on top of that, on top of write-back caching, they implemented an object packing strategy, which basically would mean, if you're familiar with the performance of S3 object storage generally, especially on Ceph, we're not particularly good at storing lots of small objects with random I/O. If we could convert those objects being ingested into sequences of much larger objects that we can write sequentially, that would increase, it turns out, our efficiency writing them a lot. I mean, that's kind of a sort of known result from storage, but Ur Kanar's dissertation shows just how much you could accelerate it with Ceph in particular and RGW if you were doing that. And so we're going to talk about a couple other things that relate to our sort of R&D in RGW that ties together with this. What basically the precursor for that is that we're interested in figuring out ways to come up with a first-class implementation in the main line of Ceph object storage that has these capabilities. The student research work has, it's sort of a student project with a lot of pieces and a lot of serial code. We wanted to fit it into an extensible framework that can be the foundation for productization and upstream and downstream Ceph. So one piece of that was figuring out how to extend this, the work, essentially the access and I/O paths of Ceph RGW in the cluster with new behavior that, for example, that can indirect into the cache, see whether something is cached already and whether we should and where to get it, or decide whether it should be in the cache, that can organize the cache replacement and all of that. So the technique we're using to do this is the zipper refactoring for RGW. We now have the ability to have different backends for data, not just Rados. That was important because some of the data most of the data in the D4 cache is in S3, but not the Rados cluster, but some other device. We might have some other kind of elastic cache also. And Zipper allows us to access these different backends from the same requests. It also has a filter, the driver extraction, from which we can, for example, inject into the lookup for the objects in the cache or to direct them there. And all of those pieces are different kinds of Zipper drivers that are being put together now. For backends, we already a year ago had people experimenting, writing new backends for RGW, so wholly new data stores, sort of like Rados, but in these cases, but not using Rados. So we have established that that RGW can have backends other than Rados, and we are working on these internally. My teams are working on these. There's a prototype of such a backend called DB Store. But more interestingly for this talk, we have these cache injector or cache adapter filters that for our purposes mainly do D4N, but there's also a precursor that's a simpler sort of processor architecture like cache called D3N for people that are interested in building a cache on a group of racks with consistent hashing. And Daniel of my team is is working on a POSIX file driver as well. We are building new front ends that are also designed to converge on the kind of workloads we've been talking about. The Spark ecosystem Apache Spark is sort of the newer big analytics framework post Hadoop. There's lots and lots of things done with it. Over time, it's developed a variety of interesting technology, data formats, with new structured data formats like Parquet, tabular data formats with indexing and synopsis, to enable data skipping, and efficient data serialization formats. Apache Arrow is also a wire data format that's very efficient. When we do predicate pushdown with S3 select, it turns out that essentially a bottleneck for returning results is the inefficient serialization of that data. The solution for that may be to use the native Apache Arrow wire format to deliver data results, and we can do that we can do that and also integrate natively into this, for example, the Spark ecosystem by using Apache Arrow Flight, which is their RPC request reply protocol.
And the way I like to kind of explain this is, if you have a bunch of objects that are stored, like say you have CSV files, and you need to do a select on it, you only care about a particular column. So pre-select, right? So if you don't, in the world before select, you would do get object, and you would get the entire thing, and then you would have to filter all the data, or you would have to do it by an offset, right? With S3 select, if you have CSV data, you can have that filtering done on the S3 side. But if you're using a more sophisticated data format, if you're using something like Parquet, well, Parquet has data broken up into pages, and it's going to, usually the framework is going to do a ranged read of the object instead of doing a full get object request, and it's going to request the compressed data, and that compressed data is going to come across the wire, and then Spark is going to do the filtering. Well, if you do the push down of select processing to, say, analyze data that's written in Parquet, if the compression is too effective, and then you filter the results, but then you return the return the results in an uncompressed format like CSV, right, which is the current status quo with select, then you're actually amplifying the amount of data that you sent back, because even though you're filtering it, that filtering is at odds with the fact that you've decompressed the data and you're not sending it back. But if instead of sending the results back via CSV, if instead we send it back with an arrow, now it's like nice, compact, serialized data that we avoid that amplification, that amplification problem. And then arrow flight takes it even one step further, right? So who here is familiar with NFS? Lots of people. Who here is familiar with parallel NFS? Right? Okay. So what parallel NFS is to files, arrow flight is to tables. Right? So instead of a client going to a single endpoint to get the data that corresponds with tabular data, it can parallelize that access. So this is where it starts to get really interesting, right? So now you have a client to cluster protocol. Aeroflight is a client cluster protocol for tables. And when you combine that with computational pushdown, really interesting.
Yeah, excellent. So he stole thunder with PNFS, but that's all right.
Oh, sorry.
No, that's cool. That was better than I would have been able to do there. So we have a vision to productize these things in a coherent way that's flexible and extensible and has a variety of dimensions that play well together. Historically, RGW is kind of it's a pretty stateless system, aimed at doing object storage IOs on Rados clusters. With the integration of D4N in particular, we end up with a richer system of primitives as well as the capabilities to do what the D4N is the state tracking and things it's doing itself. So we have a Redis directory cluster converged on an RGW cluster. The D4N project in particular is going to use that, or the technology is going to use that to maintain an ephemeral directory of the objects in the cache, also all the metadata and history and information that's going to be needed for the replacement algorithms or admission policy that it's going to run. We end up with a DAGO with it, so an intelligent prefetcher that knows about actually interesting workload scheduling and algorithms that workload's that say Spark is going to produce. And we have hopefully an extensible strategy for bringing that to more kinds of processing. We potentially have an object packing implementation, which is something that a lot of large, just archival sort of workload S3 consumers have told us was critical for them, and we know to be critical. And we have, in the way we're putting together, hopefully, a lot of flexibility from the way we've gone about implementing things, Zipper and other things. We have a bunch of front end, we have flexible front ends that correspond to alternate strategies that different applications want to do to most efficiently access data, not just S3, which is good for some things, but there's a lot more potential there. Arrow in particular, as we've emphasized, and there's also a quick front end. This is a more or less totally orthogonal, but not completely. When we first started seeing very large workloads coming from Hadoop in particular, but also large backup systems and other things, what became immediately obvious is that S3 imposes a requirement for a very large connection density from clients. Like hundreds of connections are needed just to handle the full cross-sectional bandwidth, I guess, of the QCT cluster testing that was done in 2017. We needed over 1,500 simultaneous TCP connections in a mesh to the RGW cluster to sustain the I/O that those clients were trying to perform. That's one of the things that the Quick protocol is designed with multi-streaming is designed to solve. A much smaller number of associations with multi-streaming can avoid head-of-line blocking, and we don't need to build up this giant application layer network front. So it should improve efficiency for both ends for both the RGW cluster and the application cluster significantly, I believe. We have abstract cache backends, so data can be cached in Rados pools of different speeds, or it can be cached in a 4 and S3 cluster, or it could be cached in an elastic cluster of say, flash caches, which is something that D3N provided us. And so we potentially have the ability to pop up caches in front of both data lakes, but maybe other workload clusters that people have that are just doing general S3 in other ways. We have abstract cache strategy implementation. This is something that people wanted out of D4M, but it doesn't exactly have, even though it has a couple of strategies. We're working on that now and incorporating it into our version of the D4N filter that we're upstreaming. We hope that not only we'll be able to use the cache algorithms that the students have prototyped, but you'll be able to write new ones and maybe write them even in scripting languages or loadable modules so that you could experiment with new cache replacement, cache omission policies, and plug them into a kind of a research basis of D4N as a system. So dynamics,
making it more making it more composable, right? So
all these things composable on these different layers. No, that's fine. So we've brought in. I've talked about zipper filters and cache drivers and different stuff. We have both. We have for most of these we already have dynamic loading for them, or we almost got that. And that would let you write a module that plugs in and does your new cache backend, or it does your new filter, or it does your new strategy. But you also might be able to script it. We've added scripting to RGW over the last few years as a way to make it even more flexible.
All right. Probably no questions, right? Nobody has any questions. Anybody? Oh, I was kidding. You can have questions. Yeah. Matt and I get really excited about this stuff, so. Yes, sir.
What can I tell the people that still use Hadoop in our company?
I mean, they can use the tools they're familiar with, I suppose, right? Like there are better tools, right? Depending on what they're doing, but if it's not broken for them, I'm not gonna tell them wrong. I probably wouldn't use it for, I wouldn't try to run a verticalized Hadoop cluster anymore, but there's a lot of times there's inertia, right? And so overcoming that inertia is often more than just a technical argument, right? There's a lot of politics involved and that sort of thing. So it can be tricky, yeah. Yeah, slowly but surely. Or if you have other groups that are doing a really good job of using other things, use them as this is the exemplary way of doing this. Hey guys, look at what your peers are doing, or point them to what kind of like the best, what you see as the best in class behavior in of other practitioners and what they're talking about in conferences and that sort of thing. Yes.
Since there is coming a lot of interesting features for Rados gateways, I wonder backwards compatibility for my existing running Ceph cluster and the new Rados gateways. So how far I can stretch that thing?
We don't want to give up. That's hopefully not going to be a big problem. I mean, there's ongoing Rados schema, RGW Rados schema themes, but we're not abandoning Rados. We continue to add new capabilities to the Rados data layouts of RGW. We're trying to improve them. I mean, I was talking to a few people outside of these meetings. One thing that Erica Boncic of my team has been working on in response to customer issues of different kinds is working on schema checking and schema repair tools. So we've been doing that for 3 years. We have the ability to find orphan objects and reconstruct and remove those without damaging that data that's in use. And we've now got the ability to recover the indexes or recreate indexes from the data that's on disk regardless of how it was uploaded. And those are the kind of round-trip engineering you need for a robust system.
Yeah, I mean, I guess a good example is some of the really old versions of Ceph. When you wrote objects into them through the object gateway, it didn't actually stripe the S3 objects over Rados objects. It would just, you uploaded a 64 meg file, it would be a 64 meg Rados object. If you uploaded a bigger object, it was just one-for-one S3 object to Rados object. And there's people that have those clusters, and they're still running, and they've transferred, through all the different releases. So the rules apply around, you can't take an Argonaut cluster today and upgrade it to Reef tomorrow. That would probably not work out well. But as long as you kind of follow the rules, there's the upstream testing in place through Toothology to make sure that we're not doing things that are going to damage the schema, and things still happen. So there's ongoing work to make sure the tools are available to deal with those sorts of situations.
Yeah, and I think it's fair to say that Rados is our premier large, scaled elastic data at rest format. We want to do more with it, not less. And we were having some conversations around deduplication within RGW. Those would be Rados. But when you start looking at things that are the I/O patterns and performance domains that are very different, or integration with other kinds of data sources, those may be invitations for other kind of backends. Or very different deployment environments like Edge. Those could be used. Those could be scenarios where we want different backends. But the layering and stuff, that's just extra flexibility we can bring to all of these.
Yeah, and like for the being able to support different backends other than Rados is an ecosystem. It's an ecosystem play too, right? So if we have other people outside of the Ceph community that are taking Ceph's object gateway and putting it in front of other systems, then there's other people that have a vested interest in improving it and making it be the best, best open source S3 implementation. And we think that's important. We think that's good. And if we have a bunch of different backends, right, then we have tools like Lifecycle. We can move data from other systems into Ceph clusters, too, right? So, yes, sir.
Yeah. Would you need to stretch the S3 API to support things like D4N or anything like that, or is it still going to be vanilla?
We generally try to figure out ways of doing things within the confines of the S3 API. In certain cases, you need to have additional interfaces. So, for example, the Caris cache prefetching needs to communicate information to the cluster. That's very trivial. That's like a necessarily like a sideband type thing. That's not necessarily going through the S3 API.
Well, it actually was. Yeah,
oh, was it?
Yeah,
I take it back.
We've done a few things like this. Like we added unordered bucket listing for S3. That's useful for a number of things. So we added some simple I forgot extra headers or something. We added a couple of extra techniques for ordinary GET requests that accomplished cache hinting for D4N. I should say that at least one of the researchers had a tendency to just cat files to suck them out of S3 rather than running the hints. But we added a hint API for that. But basically, also I would say Oran Krieger, the Boston University professor I mentioned here, his vision is to all S3 all the time. S3 as a lingua franca for cloud storage. I'm not sure if that's permanently viable, but I mean, there's going to be need for other things. But really, though, no, we have not been trying to bend S3 to do different jobs. Although we talked about Aeroflight, that's something that comes from another data community, another storage community, and we want to converge with it. But we haven't been trying to change S3.
Yeah, and in some cases, we'll try to do something clever where I usually refer to it with Matt as like API smuggling, where we put something in via a header, or we overload some sort of, to communicate the need to do some sort of behavior without like creating full new like API verbs, right, that aren't supported in the SDKs and that sort of thing, right? Yes. Tape driver.
This is the week of tape.
I mean, if we have a POSIX backend for the RGW, and there's an enterprising individual that puts it on LTFS, I don't know. We could see.
Yeah, people have also discussed zipper filters for tape. Yeah. People seem interested in doing tape.
Yeah, there's a lot of interest there.
Pardon?
Sorry?
I don't think anyone wants to do paper tape. Do you want to do paper tape? It's very slow.
At IBM, we may have dot matrix. We could.
Any more questions?
Thank you, everybody.
Thank you. A lot of fun.